Welcome to the Math Record. Today we'll be covering the second video on the graphical aspects of derivatives. This video will cover part 7 of chapter 2. In this video, we'll be covering concavity and inflection points, along with the concept of higher level derivatives. Okay, let's begin with concavity. So, as you know, there are two types of concavity. There is concave up, right, which is like this. This is going up, right? So it's opening up. And there is concave down, right? Which is like this, because it's opening down, right? So those are our two concaves. So how do we know if a graph is concave up or concave down? Just doing the math without actually like looking at a picture. Well, all we have to do is technically look for the second derivative. So what is the second derivative? Well, basically, it's just a derivative of a derivative, right? So in our original equation, let's say we have f of x, right? If we take the derivative of that, we have f, right? We have this apostrophe there. Now, a second derivative, we just write a second derivative like this. This is referred to as higher order derivatives, because now you have more derivatives, right? So this is referred to as our first derivative. And our second will be referred to as our second derivative. Our original graph is just called our original function. Okay. Now, if you want to find like the third derivative, you could like have 3 apostrophes. This would become our third derivative. But by this point, you could usually just use like f of 4x to refer to as your fourth derivative. Right? And so on and so on. So if this is like the fourth, f is our fifth, x is equal to our fifth derivative, okay? So even if you want here, you could just say f is equal to 3x. But usually if you want to write it as notation, you could just have it as 1 apostrophe, 2 apostrophe, and 3 apostrophe for first derivative, second derivative, and third derivative, right? But after that, it's too much apostrophes and you just start using these. So in case like anyone gets ever confused, you could just say that this is a derivative and you could just label it as such, right? So you could say the fourth derivative, you could say this is the fourth derivative, right? Etc. Right? I'm not gonna write the remaining out because I don't have room. So that's the concept of higher order derivatives, which is basically taking your derivative of your derivative, right? So our first derivative, taking a derivative of this derivative, we get the second derivative. Now take the derivative of the second derivative and you get the third derivative. Now take the derivative of the third derivative, that's going to be our fourth derivative. And that's basically how it works. Okay? So let's go back to concavity. How do you find concavity? Well, if you're given a graph, which let's say is f of x, this is your graph, right? And you want to find the concavity of f of x, then all you have to do is look for the second derivative of f, right? So for the second derivative, if part of the graph is greater than 0, it's gonna be concave up. Okay? And if the graph is less than 0, it's gotta be concave down. So it isn't always concave up, and it isn't always concave down. It's gotta be a mix between all of them, which is most cases. Some cases is not, but basically it's if we have graphics like cubics and highers, we have things like this, right? So we have like a concave down, a concave up, a concave down, a concave up, and a concave like down and a concave up, right? So we always have these intervals of concave up and concave down. And to do this and to find where they are, we just use derivatives, which most precisely the second derivative. And whatever is above that graph is concave up. Whatever is above the x-axis is concave up. Whatever is below the x-axis is concave down. Okay? So let's use the equation which we use in the first part of our video of chapter 7, part 7. So we have f of x, which is equal to 2x to the power 3, right? So 3 minus 9x squared. Oops. Okay. Squared plus our 12x plus our 6. Right? And now if we take the derivative of this, then we have 6x squared minus 18x plus 12. Now we take the derivative of the derivative, right? We have 6 times 2 is 12x. And the derivative of 18x is just minus 18. Right? And now we just have to find the intervals. So the first thing you have to do is that you're going to have to look for the x-intercept of the second derivative. So 12x minus 18 is equal to 0. Right? So the x-intercept is x is equal to 1.5. Okay? So we're just going to write this on the side so we can save room. Minus 18 is equal, so x is equal to 1.5, right? So now we have our domain, okay, I forgot our domain restriction. Let's say it's from -2 to 5, right? Same as our example in part 1 of our first video in part 7. Now our domain restriction is from -2, right? From -2 to 1.5, and from 1.5 to 2, right? So those are our two intervals. Oops, sorry, to 5. Okay, so always put your intervals. If there's no intervals, then basically just say it's like -infinity to 1.5, and from 1.5 to infinity. Okay, so now you have to find out what is the values that that goes into the second derivative and see if it's positive or negative, right? So we have -2 to 1.5. So what value can you put in? Let's say we could put in 0, right? Because 0 is between -2 and 1.5. So we put in 0, we get 12x times 0, which is 0. And then 0 minus 18 is -18. So that's negative. So in this interval is negative, right? So as we said, if the graph for the second derivative is below the x-axis, then it's going to be concave down at that point. So from -2 to 1.5, it is concave down. Okay? We're not saying that the derivative is concave down, or the second derivative is concave down. We're saying our original function is concave down. Don't mix that up, because the first derivative and the second derivative is not concave down. It's only the original function. So let's say now we have 1.5 and 5. Let's choose a number. Let's say 2, right? Because 2 is between 1.5 and 5. So, and if we plug in 2, 12 times 2 is 24. 24 minus 18 is 6, right? So 6 is positive, right? So as we said, if the graph is positive, it's above the x-axis, right? If it's above the x-axis, that's concave up. Up, right? And that's basically all you have to do, which makes sense, right? Because if we have a cubic, right? 2x cubed minus 9x squared plus 12x plus 6, which is just a cubic function, right? We have something like this. So at this point, like right here, let's say this is 1.5, right? Then this is concave down, right? The first part is concave down from -2 to 1.5, and then 1.5 to 5 is concave up, right? So it makes sense. Okay, so that basically covers everything for concavity and how you can find it using second derivatives. And now let's move on to inflection points. So what is an inflection point? An inflection point is basically a point where the concavity changes. So it either changes from concave up to concave down, or from concave down to concave up. So that's an inflection point. So how do you find inflection points? Well, all you have to do is that we already did this in when we were looking for concavity. You basically just look for the x-intercepts of the second derivative, right? So if you're having if you have f of x, right, and you're looking for the inflection of f of x, then all you have to do is that if you find the second derivative of that function and you look for the zeros, right, then you're right. Then whatever x value that is going to be an inflection point. So in our original function, we have f of x, right, which is equal to 2x cubed, which we're using our same example again. So 9x squared plus our 12x plus our 6, right? And we said our first derivative is equal to 6x squared minus 18x plus 12. And our second derivative is equal to 12x minus 18. Sorry about the handwriting. And now, basically, we set our x equal to 1.5, right? This is just similar to what we did before. I'm just rewriting it again. So what it tells us that the 1.5 here, which is the x-intercept of our second derivative, right? Our second derivative. Then basically, x is equal to 1.5 is where our inflection point is at for our f of x. So x is equal to 1.5 is our inflection point at f of x. And it's basically all that simple. That's all. It's basically just that simple. That's all you have to do. So that's how you find the inflection points. Which makes sense, right? Because technically, when we were doing our concave ups and our concave downs, right? We had our cubic functions, right? Our cubic. Now this is concave up and concave down. So where does it change concavity? Well, at the inflection point, right? So at this is our inflection point, then from, right? So from here to here is concave down. And then we have from here to here is concave up, right? Because the inflection point tells us where our concavity changes. So our inflection point tells us where our concavity changes. And that's your general idea of basically how to find concavity and inflection points using higher level derivatives, which is basically only using the second derivative. But if you're working with higher level derivatives like the third, fourth, and fifth, it's not going to be used as much in calculus, but it's going to be important later on when you're trying to prove a bunch of interval concepts, which we will tackle later on in later chapters. Well, that basically completes part 7 of chapter 2. Thanks for watching, and I'll see you at the next math card.